Hello guys. So apologies. This should be out on Wednesday. I was kind of sick this week, so I'm not able to record the video previously. But yeah, anyway, let's start with the part two of the section 16.3. So let us first recall what we have done last video. Basically, we have derived the fundamental theorem of line integration, which is actually a very direct result from the fundamental theorem of calculus in one-dimensional calculus, and basically states that whenever you're evaluating a vector field, which is conservative, or a gradient vector field, those are the same thing, over a particular curve, then the result will simply be the potential function evaluating at the endpoint, subtracting the function evaluated at the starting point. Okay. In particular, it will be path independent, meaning that the line integral over every path with the same ending point and the starting point will be of the same value. Okay. And we actually do some example and derive a very nice theorem about conservative vector field, which is saying that over a connected open set, that is a set which every 2 points within a set can be connected with a path within the set, and also openness means that basically the set does not contain its boundary. So on that nice property, the set with this nice property, and any vector field which is defined on that set, then the following three statements are equivalent. The first is saying that the vector field F is conservative, meaning that vector field F can be written as a gradient of some function. Secondly, the line integral of this function over any path, with the path being simple and closed, then the line integral will vanish. The third statement is that we have path independency, meaning that for every two paths within the set omega with the same starting and ending point, then you always get the same line integration. So those three are equivalent statements and is one of the criteria for you to distinguish whether the vector field F is conservative or not. And we have spoken last week that these are not really useful criteria per se, because it is not really able for you guys to pick every path within this omega and evaluate a line integration, right? So there should be some sort of more computable arithmetic type of criteria, and that is true. We call it the Poincaré theorem. So today, then let's start with this Poincaré theorem, and then we'll go on to the examples of this Poincaré theorem. Okay, just to note that the proof of this theorem is not included in the textbook. I included it for completeness, but again, the proof itself is not important. The important is to understand the theorem itself and how to apply it. So let me state the theorem. So now we have omega be an open set. In this case, let me emphasize that we're dealing with R2. I will state the version for R3 later, but it is slightly different. So we state that F is now a vector field given by P and Q. P is the X component and Q is the Y component. So it is a continuously differentiable vector field, meaning that the differentiation of P and Q are themselves continuous. So we state that if F is conservative omega, then you must have the differentiation of Q respect to X, the Y component taking derivative respect to X, and the X component taking derivative respect to Y must be the same. Okay, we have actually proved this last time in the line integral video, which is 16.2, that this is actually a direct consequence of Claire's theorem. The second one is the most important one. It is basically what Poincaré states. So whenever omega is similar connected, we will review this later afterwards. So if basically omega has no holes, and that the function P and Q satisfy partial Q partial X is equal to partial P partial Y, then it is conservative. Okay. So in some sense, the first statement states that whenever omega is conservative, then you always have this necessary condition, meaning that you can always give this equation to be true. On the other hand, to prove that it is sufficient, we need to include the similar connected condition, basically stating that on a nicely enough domain, and if the components of this vector field F satisfy this equation, then it must be conservative. Okay. So you see that the sum condition here is actually really useful because you can basically check the differentiation to verify whether f is conservative or not. Okay. So let us start the proof first, and then we'll do some examples. So the first statement is, again, as I mentioned, we proved it last time. Basically, it follows from Claire's theorem. So suppose that the vector field is indeed conservative, meaning that f is given by gradient f, right? So what is partial q partial x? By definition, since q is the y component for f, it is basically the partial differentiation with respect to y of this f, right? So you have partial q partial x being partial x over partial f partial y. And Claire's theorem tells us that as long as this is continuous, which is assumed in our statement, then you can exchange the differentiation in an order. So in this case, partial x partial y will be partial y partial x. And then again, by definition, this guy is simply p, right? So we have partial p partial y. So as long as f is conservative, then it always has this equation to be true. Now, on the other hand, let us prove this Poincaré theorem, which is the proof is actually really elegant. So first of all, let us remind what is simply connected. So simply connecting basically means that given any path C0 and C1, we can obviously reparameterize it to make those curves to be of the domain 0, 1. So for all those two curves with the same starting points, let's say C0, 0 and C1, 0 are both P0, and C0, 1 and C1, 1 are both P1, so they have the same starting point and the same ending point. And simple connectivity of a set is saying that for every these two type of curve, whenever they have the same starting and the ending point, you can always find a so-called homotopy, which is a function defined on 0, 1 cross 0, 1 towards omega that sort of modify the C0 all the way onto C1. And to be precise, this is how this homotopy works. So first of all, the first variable here encodes the time. So basically, this t is the same t as this guy. So that means, let us see here, we require that this h satisfies ht0 to be c0 t. So the second variable, let me denote by s here, means the number of the curve. So the 0 corresponds to the 0 here. And similarly, we require that ht1 is equal to c1t. Okay? In this case, we denote the 1 here to be the number. So different number here gives you different curves. For example, you see I drew it here. This is ht.1, ht.5, and ht.9. And we also require that all these curves share the same starting and ending point. So basically, h0s must be p0 and h1s must be p1. So that means that every curve has the same starting and the same ending point. Okay, this is what homotopy means. So it is basically a bunch of curves that is within these two curves, and it translates from C0t all the way to C1t. Okay, this is called homotopy. And geometrically, having a homotopy for every curve simply means that you have no holes. Because if you have some hole, then you cannot create such homotopy, right? You must have some discontinuity in the middle. So that is homotopy. And now we will show by this homotopy equivalence that we actually have this Poincaré theorem. Okay, so let us clear our minds and let us try to think what we should be proving. We want to show that as long as this equation is true with the simply connected assumption, then f must be conservative. So we have already proven a lot of equivalent statement about conservativity, right? One of the useful statement will be path independency. So basically, given two paths with the same starting and ending point, we want to show that you have the same line integral along those two curves. And that is what we will show in this proof, okay? So, yeah, basically, given C0 and C1, we want to show that their line integral are the same, provided you have the equation partial q partial x is equal to partial p partial y. So let us start the proof. We define here some auxiliary function defined by a t of s. So there's two variables, t and s, defined by this formula. We define a vector field f evaluated at ht of s. So hts basically means the s curve at the time t, right? and we take dot product with the partial differentiation of HTS respect to t. So this is basically the speed of the curve S at the point t, basically. And so we take the dot product. And similarly, we take a sort of a symmetrical thing. We take f of h of ts, taking dot product with partial h, partial s. Now we're gonna prove a theorem. We're gonna prove an equation, which is we're trying to prove partial a, partial s is equal to partial b, partial t, which will be useful later words. So let us first start a proof. Let us see what is the partial differentiation of this guy. So by product rule, excuse me, let me drink something. Okay, so by product rule, we know that even if this is a dot product, you can still do that entry wisely. And basically, it becomes taking partial differentiation with respect to this guy here, and then taking partial differentiation with respect to this guy. So you have partial f, partial s, taking dot product with partial h, partial t, together with f dot partial squared, partial s, partial t, h. Okay. Now, what is this guy? F of h is simply P of h and Q of h, right? Don't forget that we are assuming F is a two-dimensional vector field. So we have by chain rule, the usual chain rule, that the differentiation of this guy, F respect to S, is simply gradient of P evaluated at h, and then differentiating h respect to S, taking dot product, right? This is the differentiation of this guy. And similarly, the differentiation respect to this guy of S is given by gradient of Q evaluated at h, taking dot product with h differentiated by S. And this guy remains, and this guy remains, right? So now let us expand everything out. It'll actually just be algebraic stuff. So suppose the coordinate of h, capital H, is given by little hts and gts. Then we can see by definition, you have the first component being px evaluated at capital H, taking dot product with the first component here, which is h differentiated by s. Similarly, the second component will be py evaluated at capital H, and then taking product with gs, right? And finally, you have the x entry here. The x entry will be ht, right? ht. Similarly, for the second term here, you have exactly the same thing. You just replace p by q, right? P by q, p by q. And then this guy will be g, because you're taking dot product with the second component, g here. Okay, so now is where we include our condition. We know that the differentiation of q respect to x is the same as the differentiation respect to, of p respect to y, right? So py here can be given by qx, and qx here can be given by py. How is that useful? Now we can rearrange our term to put, you see, this guy is still the same here, but we make this guy pyhsgt to here, and it becomes pygths. And then we put this guy here, which is qx now, to the second bracket, and you get qx/ht/gs, which is the same term as this guy, right? How is that useful? We see that basically you have the same term, but you're differentiating respect to t first, and then s, right? So that'll be basically the partial differentiation of b respect to t, by definition. So let's go through this again. We define two different functions in terms of t and s, given by f evaluated at h, taking dot product with h over t. And this is kind of motivational because this is what the actual line integration looks like, right? And we define an auxiliary function bts by the same thing, but we differentiate with respect to s, but not t. And what we show here is that the derivative of a respect to s gives us the same thing as the derivative of b respect to t. Okay, so this is what we obtain. Now let us try to see what happens. So recall that we want to prove that the two line integrals share the same value, right? So the idea will be to take a difference and to see whether it is 0 or not. So by definition, the line integral of f over c1 is simply f c1t taking dot product with c1 prime t, right? dt. And respect to c0, it is oh, sorry, this should be C naught, not C2. So respect to C naught is simply F evaluated as C naught taking dot product with C naught prime T, right? However, by construction of that homotopy, basically had that this guy is HT1, right? And this guy is HT naught. The same thing happens here because C1T is simply HT1. So we have the partial differentiation of this guy respect to T and a partial differentiation of this guy respect to T. And you can see my blue line here, this guy gives us AT1 by definition, and this guy gives us AT0 by definition. So again, by definition, actually by fundamental theorem of calculus, we know that AT1 minus AT0 respectively, if you regard that as a one variable function, then it is simply partial A TS, partial S, integrating over S from 0 to 1, right? That is the definition of fundamental theorem of calculus. You have this guy taking differentiation and integration, so this will be an antiderivative. Plugging in the corresponding endpoints 1 and 0, you will get this guy and this guy, right? So we basically now rewrite this difference to a double integral, where the integrand is partial A, partial S. Now, it is useful for our previous identity. We see that partial A, partial S is given by partial B, partial T, right? And we change the order of integration because this is only square, 0, 1 times 0, 1, right? So you have actually no really big deal by changing the integration, again, from dt to ds. And by definition, again, by fundamental theorem of calculus again, you have this guy to be B1s minus B0s ds, okay? However, let us see what B looks like. B is simply given by f of h dot partial h partial s, right? However, if you evaluate it at 0, you have 0 here and 0 here. But what is h0s? That is the starting point of the curve enumerated by s, right? But the starting point for every curve is the same. So this guy is always P naught, right? Making that this thing actually does not depend on s. So the derivative is actually 0. So this will be a 0 vector, basically. And similarly, B1s has this term, but this term always represents the endpoint, P1. So you again have the same thing, which this guy will be a 0 vector. So B1s will still be a 0 function. So both of these guys are 0 for every s, making this difference to be 0. So we see that based on the similar connected assumption, this two line integration will always be the same, provided you have that nice formula, Py equals to Qx. So at the end of the day, what we have concluded is that f will be path independent, okay? And then by our previous equivalent theorem, that implies that f is conservative, okay? So this is actually not a really difficult proof. It is basically just commutation and an application of this similar connectivity. So if you're interested in this, I really encourage you to try to do this yourself, because if you actually do the differentiation, you will see that it is nothing but a bunch of chain rules and identification of different differentiations. Right. So anyway, what we have to take back is that Poincaré theorem basically tells us that if your domain is nice enough, then this property and f being conservative are equivalent, okay? So we can basically verify whether f is conservative or not based on this equality if we're working on a nicely enough domain. So I want to make our last remark here. Basically says that simply connected domain are domain without hole, okay? So we have a very complicated definition for simply connected domain, right? For every two curve with the same starting and ending point, you have a so-called homotopy that modifies C0 towards C1. But basically, that means that the domain has no hole, because if you have a hole, then you don't have a homotopy. If you don't have a hole, then you always have a homotopy, basically. So, for example, a unit disk in this case, for every xy belongs to R2, we restrict x squared plus y squared to be less than 1. That is an open disk, right? That disk is obviously semi-connected because there's no hole within the disk. However, for example, if we take the puncture plane, meaning that we take out the 0, 0, the origin from the R2, then this is not semi-connected domain because there is a hole at the origin. So for example, every curve that looks like this cannot be homotopic translated onto the other curve because you will be stopped somewhere here, right? So take in mind, basically, we intuitively in the Poincaré theorem is saying that if you're working with a domain without hole, then conservativity is equivalent to the equation Qx equals to Py. Okay. And again, with the exact same strategy, actually, you have this similar three-dimensional line integration conservativity theorem, the Poincaré theorem. It states that whenever F is now a three-dimensional vector field, PQR, then the following are equivalent. So whenever you are working with a simply connected domain, then conservativity is equivalent to these three equations. The differentiation of q respect to x is equal to the differentiation of p respect to y. And so is the similar identity here. We will give a better kind of description for this condition here. The words, this is actually called the curl-free vector field. So based on that kind of terminology, we're saying that curl-free is equivalent to conservativity, basically. But yeah, that is for afterwards terminology. But this is the condition being conservativity. Okay. So let us work on some example to show how powerful Poincaré theorem is. So now we have some vector field defined on either R2 or R3, and want to distinguish whether it is conservative or not. And if it is, we want to find the potential, basically the function f, so that the capital F will be the gradient of this function. So this function y, x squared y, is actually given previously in this example. Let me go back here, this example. So for this example, to prove that it is not conservative, we actually show that there is some non-zero integration over a closed simple curve, because that is what conservativity requires, right? Conservativity is equivalent to having a vanishing line integral over a simple closed curve. But in this example, we show that there is some non-vanishing line integration. But now we actually have a more efficient way to do this. So we can simply take the derivative of this guy with respect to y and this guy with respect to x. And we see that, oh, actually, sorry. I did the wrong thing here. Partial p partial y is 1, that is correct. But partial q partial x should be 0. My bad. So the differentiation, oh, yeah, sorry. I did it correctly, my bad. This is q. So you do the differentiation with respect to x, you get 2x1. So we see that partial p partial y is not equal to partial q partial x. That means that you don't have a conservative vector field. Okay? And don't forget that we are now working on Rn, which is the whole space. The whole space is definitely simply connected, okay? Because there's no holes. And for the second vector field, y ex plus sine y and ex plus x cosine y, let us check the differentiation. So if we differentiate this guy, p respect to y, you will get ex plus cosine y, right? And we differentiate this guy respect to x, you'll get ex and then plus cosine y again. So they're the same. And since Rn is similarly connected, Poincaré's theorem tells you that f is conservative, right? So based on that, we can now try to find the potential function. So this type of checking actually ensures you that there will be a solution of this integration problem. Basically, we want gradient f to be capital F, right? So fx will be the first component, which is this guy, and fy will be the second component. So now we have to do this all the times. That's video. We do the partial integration. So in this case, we do the partial integration with respect to x, and you get y ex, the same thing, plus x sine y, and constant term with respect to y, which is any function with respect to y. Constant term with respect to x, which is any function with respect to y. The same thing happens for the second line. You get again y ex plus x sine y plus g2x. So we see that these two functions must be an absolute constant, meaning that f of xy, the potential, should be written as y ex plus x sine y plus some absolute constant c. Okay, these are all potential for these vector fields. Right. Thirdly, we want to distinguish whether this vector field is conservative or not. It is given by yz, xz, and xy plus 2z. So I want to emphasize that this, you don't really have to memorize this, because if you have the idea of Claire's theorem, then it basically is saying that the double differentiation should be commutable. So this is basically, say, partial square f, partial x, partial y, and those two should be the same. The same thing works for these two guys. So that is right. We see partial q, partial x, in this case, this guy gives us z. And partial p, partial y gives us, again, z. The same thing happens for the latter two term. The required equality are the same. So we see that, again, by Poincaré's theorem, and the fact that Rn, in this case R3, is similarly connected, we know that the function field, the vector field here, is conservative. So it remains to find the potential function, right? That is what required in the problem. So we see that we require fx to be yz, fy to be xz, and fz to be xy plus 2z. So by doing the partial integration, we see that f of x, fxyz is given by xyz plus some constant respect to x, meaning that it is any function with respect to y and z. The same thing happens for the latter two terms. You get xyz plus g2 xz, and then xyz plus z squared plus g3xy. So by comparing these two equations, we see that we should have g1 and g2 to be z squared plus c, and g3 is simply some constant. So at the end of the day, you get f of xyz to be xyz plus z squared plus c, which is kind of intuitive, right? Because you see that if you differentiate this guy with respect to x or y, then this term will vanish. This is why we always include these two constant terms. The constant is with respect to the x or y, but not the whole variables. So this will be our potential for this vector field, right? Now, let us do, I think this is our last example. Yeah. So this is a very classical example. It shows the necessity of the domain being similarly connected in Poincaré's theorem. So in this case, I define the vector field f given by minus y over x squared plus y squared I plus x over x squared plus y squared j. Obviously, the denominator cannot be 0, so this whole thing is defined on R2, taking out the lower origin. And this is the puncture hole I just mentioned before, right? So in the first problem, we will show that it actually satisfies the requirement for Poincaré's theorem. So this is actually very direct. You differentiate this guy by the q by x, which, oh, my bad. This should be x and y. So we differentiate the q by x, and you get this guy. And by doing the usual, in this case, quotient rule, you get y squared minus x squared divided by x squared plus y squared squared. And by doing derivative respect to this guy, you'll get, actually, there should be some minus. Let me check what am I doing correctly. Oh, yeah, sorry. Yeah, this is p. Yeah. So p is minus y over x squared plus y squared. And we differentiate p by y, you will get the whole thing here, and it simplifies to the same thing as the qx. So we actually have qx equals to py on omega. However, this does not really imply it is conservative. So the second problem asks us to show that it's not conservative. That is cy. So to show non-conservativity, you can, as I mentioned before, find some closed curve and show that you actually don't have vanishing line integral. In this case, just for convenience, I choose the circle cosine t plus cosine t sine t, where t goes from 0 to pi. So that's a circle with radius 1 of the center origin. So line integral is given by f of ct dot c prime t from 0 to pi, right? And by definition, f is something like this, minus y over x squared plus y squared in x coordinate. So you have sine divided by cosine squared plus sine squared, and cosine divided by cosine squared plus sine squared. By doing the product, the inner product, the dot product, you get actually 1 based on the Pythagorean theorem, because you see this is cosine squared plus sine squared, that's 1. Sine squared plus cosine squared is again 1. So we see we're integrating 1 from 0 to pi, and that is 2 pi, right? So we actually have that this line integration over a closed, which looks like this, a closed simple curve is non-zero. So this vector field will not be conservative, okay? So let me emphasize on these two theorems. The previous theorem we proved in the first lecture shows equivalence of different conservativity, different properties respect to conservativity. And this thing does not require actually anything about the set, only connected and openness, which is kind of the usual assumption we assume on sets when we're doing differentiation or line integration. So you don't have to do anything about this theorem because you can simply verify f is conservative or not. In fact, verify that it is not conservative via finding some curve that you have non-vanishing line integration. And that is what we have done in this particular problem, right? We find a closed curve in which the vector field has non-vanishing line integration. And the second theorem, the Poincaré theorem, states that you must have the assumption on simply connectivity on the domain in which you can guarantee that this equation is equivalent to conservativity. So this actually explains why we have this strange phenomena that even this function, this vector field, satisfies this equation, but is non-conservative. It's due to the fact that omega here is in fact not simply connected. So there is a possibility that you satisfy this equation, but you are not conservative, depending on the domain. If the domain is simply connected, then it is not possible. But if the domain is not, then in this case, it is possible. And this shows how important the similar connectivity is for the Poincaré theorem, okay? So let's make some remark here. We see that f is actually conservative if you are working with the domain without the origin. So basically, in this case, you see that, for example, I write this down. It can be written as the gradient of the inverse tangent y over x, provided obviously when x is non-zero. And in fact, as I mentioned, it really does not contradict Poincaré's theorem because the domain here is in fact not simply connected. Okay. However, the vector field f is actually conservative on any domain like this. We cut off the origin, basically because you can define the vector field on that origin, together with the ray. In this case, I cancels out everything on the x-axis, where x is negative. Or we can do something like we cancel out anything on the straight line, x-axis, okay? Then this domain will be simply connected because there is no hole, right? Or this domain will be simply connected. And we actually show that on those domains, we have this equation. So on those domains, you actually have conservativity, meaning that if you do any line integration, say some line integration over C, which is enclosed in this origin, in this domain, so something like this, then you actually get line going to be zero. So the only possibility that you have a non-zero line integral for this non-conservative vector field is some curve which enclose the origin. Okay, so that is why I said here, if C does not enclose the origin, then we actually always have the line integration being zero. And again, for any curve that encloses the origin, you have the line integration being non-zero. In fact, it always will be 2 pi if the curve is simply enclosed. So this is a very classical example showing that the importance of the simply connectivity in Poincaré's theorem. So let us go back to what we have done in this video. We prove a very powerful criteria for conservativity of a vector field is that when the domain is nicely enough, in most cases it will be a domain without hole, then we always have conservativity being equivalent to partial q partial x equals to partial p partial y. Okay, the same thing happens in 3D. The condition is slightly more complicated, but better than checking every line integration. It is saying that qx equal to py, ry equals to qz, where pz is equal to rx. Okay. Right. So last but not least, let us go through our map on the vector calculus. So we see previously in maybe your calculus 1 course that we have this so-called fundamental theorem of calculus, sort of interchange between the differentiation and integration, right? They are like inverse operations. Now, in R2 and R3, we have developed this fundamental theorem of line integration, which is telling you that after taking gradient of a function, you get a vector field. And a line integral over that vector field is actually just evaluation of functions, right? On the endpoint and start point. So that works for both R2 and R3. And then afterwards, we will show that there's different operation of differentiation, and we can do different types of fundamental theorem of calculus to go back from a double integration or a triple integration back to a 1D integration or 2D integration. Okay, those are called Green's theorem, Stokes' theorem, and divergence theorem, which we will learn in 16.4, 8, and 9. So for now, we already covered everything here in this particular rectangular domain. Okay. All right. So I know this might be a little bit much. This is a little bit complicated in comparison to the straightforward commutation of integration and differentiation in the previous lecture. There is more theoretical part in this chapter 16, but I would say it is why it make it more interesting. It connects how we can understand the n-dimensional space and n+1 dimensional space. There is an interchange between differentiation and integration. Right. So I will see you guys in the next video, which will introduce the Green's theorem, which sort of tells you how we can translate from 2D integral to 1D integration. See you guys.